The normal distribution is incredibly important for hypothesis testing because of the central limit theorem. As you become more advanced in your scientific career and you enter the workforce, you're going to be using more than just the normal distribution, things like the beta distribution or the Poisson distribution, but especially in this course and really, the bedrock for most scientific research is going to be the normal distribution. So let's explain why that is. The normal distribution applies to many real-world situations, and it has a number of properties that you need to remember. First, it's a continuous distribution. It's not discrete like the distribution for rolling a dice. It's also not uniform like the distribution of rolling a dice. It peaks in the middle. So the probabilities of obtaining certain numbers or certain outcomes is not the same, unlike rolling a dice. It's also symmetrical. So we see the peak in the middle and the slopes that are symmetrical on either side of it. The area under this curve equals 1 or 100%. That's true for all continuous probability distributions, but the probability never equals 0. So you see these arrows here at either ends of the tail of the normal distribution. Those are very, very close to the x-axis. So it almost looks like the probability of those extreme values is 0, but it's never exactly 0. Another important property of the normal distribution is we only need two values to construct it. We need a population or a sample mean, and we need a population or a sample standard deviation. With the standard deviation and the mean, we can construct the normal distribution for any given process that we'd like to. Another important property of the normal distribution is that 68% of the area under the curve falls within plus or minus one standard deviation of the mean. Now, what does that mean in practice? Let's say you were measuring how long people's index fingers were, for example, and that variable, the length of your index finger, was normally distributed. That means that if you took 100 people's index finger measurements, 68% of those measurements would fall within one standard deviation plus or minus of the average index finger length. 95% of the area under the curve falls within two standard deviations of the mean. So again, if you measured the index finger length of 100 people, 95 of those 100 people would have index finger lengths that were between, plus or minus two standard deviations from the mean. 99.7% of the area under a normal curve falls within plus or minus 3 standard deviations of the mean. So if you measured 100 people's index finger length, rounding up, basically 100% of them, all of them would fall within plus or minus 3 standard deviations of the mean. It's a lot, but it's not exactly 100%. It's 99.7%. That means 0.3% of the population has very, very long or very, very short index fingers. Okay, it's not a 0% chance. Earlier, I mentioned that to construct a normal probability distribution, you needed two things. You needed an average or mean value and the standard deviation. So what is the standard deviation? Well, it's a measure of variability. So what is variability? The way I think of it is it's a measurement that tells me how reliable the mean is as an indicator of the expected value. Okay, now what do I mean by that? Well, I'm here in my sunroom right now. I have the heat pump set to 21 degrees Celsius, and I'm very comfortable. On average, I'm very comfortable. It's a comfortable temperature, and I enjoy it. I could also be experiencing a temperature on average of 21 degrees Celsius if I stuck my head in the freezer and my feet in the oven. On average, I'd be comfortable. But obviously, this is different because I'm really averaging two very extreme uncomfortable values, right? Freezing and burning. So the measurement of variability is going to tell me how reliable my average is as an indicator of expected value. Now, there's a number of ways you can measure variability. In statistics, we typically think about the variance and then the square root of the variance, which is the standard deviation. So as an example, in a manuscript or in scientific experiment, let's say you're measuring the weight of apples. How much does the average apple weigh? You would say that the average weighed 180 grams and the standard deviation was equal to 30 grams. And because we know this is normally distributed, we can say, okay, 68% of the apples in the world or in our sample, depending on if we're looking at the sample mean or the population mean, 68% of our apples are going to be within 150 grams to 210 grams. That's in that range, 68% of our apples will be. So how do you calculate or measure variability, variance, standard deviation? I'm going to give you some equations in a little bit, but I want to illustrate the concept first here. So we have our sample of 28 apples. We weighed them. We have the average value of these apples, 180 grams. For every individual apple in our sample, we can calculate its deviation from the mean. So does it weigh more or less than the mean? So here we have an apple that weighs 70 grams less than the mean, another one that weighs 30 grams more, another apple that weighs 80 grams more than the average. And we can do this. We can calculate the deviation for all 28 apples. And if we add them up, it's going to add up to 0, okay? Because we're going to have some apples that are less than the mean, some apples that are greater than the mean. And by definition, like the proof of what an average is that these deviations add up to 0 necessarily, mathematically. So if we want to calculate the variance, we have to square these values, because when you square a number, then negative numbers will turn positive, and then we can add things up, and they're not going to just equal 0 every time. So here we have the equation for variance. We take this is for a population, not for a sample variance, but I'll explain that in a minute. Basically, what we're doing here is we're taking the deviation of every value from the average. The mu is the average. We take the deviation, we square it, we add it up, and then we divide it by the sample size, n. This is for a population because we're not accounting for degrees of freedom like we would in a sample variance, but we're going to get there in a minute. This is how variance is calculated for a population. And to get the population standard deviation, it's very simple. We just take the square root of the variance. So if your variance, for example, is equal to 100, the standard deviation is going to be equal to 10. So that's the population variance and standard deviation. But here we have the sample variance and standard deviation, which is what you calculate when you're not measuring all the population of apples, but just you're measuring, say, 28 apples, just your sample. And here, it's the exact same equation. The sample variance is to the population variance, except we subtract 1 from our sample size, or n. And that has to do with degrees of freedom, which will be explained later. But that is the equation. And the sample standard deviation is the exact same. You calculate it the same way as you do the population standard deviation. You just take the square root of the sample variance. Now, when we take the sample standard deviation, we also call this the standard error. And the standard error, or the sample standard deviation, is basically a measure of, how much does the average apple vary from the mean? Or how much does the average value vary from the mean, more generally? Now let me introduce the central limit theorem. This is the probability distribution for rolling a 20-sided die that you've seen or saw earlier. It's a discrete distribution. It's uniform, meaning there's the same chance of rolling every single number, a 5% chance, 1 divided by 20. It looks nothing like a normal distribution. Okay, so let's say I wanted to know what the average value was of rolling a 20-sided die. Now, what I decided to do was roll a 20-sided die, or a d20, 5 times, and then record the average of that sample. And that would be considered one sample. So, for example, I rolled a dice 5 times, and my average was 15.2. And I kept doing that. I kept rolling dice 5 times and took the average of those die rolls. You can see that it's fluctuating quite a bit. Let's say I did this 50 times. Okay, now what would this sample distribution look like? Okay, this looks a lot less like the discrete probability distribution that underlies a 20-sided die roll, and it looks a lot more like a normally distributed variable, like a normal distribution. And so here you can see, my first 13 samples of 50 in the columns or the table on your left, and below me on your right, you can see the counts. Okay, now this is from 50 samples. Let's say I took 100 samples. Again, each sample is just 5 die rolls and the average of that 5 dice rolls. This looked a lot like a normal probability distribution. And when I calculate the sample mean, the average value of this distribution, it's 10.48. Very, very close to the theoretical or population distribution, which is 10.50. All right. So now you can understand what the central limit theorem is. That the sampling distribution of a variable becomes closer to the normal distribution as the size of the sample increases, regardless of the underlying distribution or population distribution that's governing that process. So in our case, the sample we took was the average of 5 dice rolls, 5 20-sided dice rolls. And if we recorded that, our probability distribution resembled a normal distribution. So, why is the central limit theorem so important? Just to reiterate, because if we take a repeated number of samples and we get the average of those samples, the distribution of the average is going to resemble a normal probability distribution, regardless of the underlying probability function. Okay, so we can go from a discrete uniform distribution to a continuous normal distribution. All right, so what has to be true for the central limit to hold? First, the samples must be random and independent. So, I'm taking 5 dice rolls and recording the average. It doesn't matter what the previous dice rolls were, the future dice rolls were. It's random and independent. Now, we need a sample size of at least 30 for the central limit theorem to apply. So I needed to roll those dice 5 times. I need to do that 30 times. So at least 150 dice rolls, basically, okay? And this is true not just for the average value. I was just showing you the average value of those 5 dice rolls. It's also true for the standard deviation. So if I calculated, instead of the average, I just calculated the standard deviation of those dice rolls, it would approximate the standard deviation of the underlying distribution as well. Now, what is the difference between the central limit theorem and the law of large numbers? Because they're kind of similar, but they are different. So, law of large numbers is that as the sample size increases, the sample mean gets closer to the population mean. And that has nothing to do with the shape of the normal distribution. So, if I rolled a dice 300 times, the average of that dice roll would probably be very close to the population average, which is 10.5. That's the law of large numbers, that, if I rolled only 10 die, the average might be like much greater or less than the true population average of my sample. So the more samples you take, the closer your sample average is to the population average. But the central limit theorem says that as the number of sample means taken increases, the distribution will resemble a normal distribution. So if you take the average values and you plot them, the distribution of your sample averages is going to resemble a normal distribution, with the mean and standard deviation of that normal distribution resembling the true population mean and standard deviation. Okay, so what is the difference between the central limit theorem and the law of large numbers? Because they seem like similar concepts at first glance. The law of large numbers has nothing to do with probability distributions. It really just says that as the sample size increases, the mean of your sample is going to resemble the mean of the true population mean. So if I only roll the dice 5 times, the average of those 5 dice rolls is probably going to be a lot different than the true population average of 10.5, just by chance. But if I roll a dice 300 times, the sample average is going to be much closer to 10.5 than if I only rolled that dice 5 times. That's the law of large number. It doesn't really look at distributions. Well, with central limit theorem is what you're saying is if you take the sample averages of your sample, the distribution of your sample averages is going to resemble a normal distribution. Okay, so that is the key difference, that we're looking at, the distribution of your sample averages. And number 2, this really only applies when sample size is greater than 30.